Hello and welcome to another session on our Introduction to Elementary Statistics. We are doing an example by hand for the chi-squared tests. We have two tests. We have a goodness of fit test that we'll do first, and we will follow that with a test for independence. So it's good in the beginning to go through these examples by hand with a calculator that we have over here, even though it is tedious. And in upcoming videos, we will show how you can streamline that, doing things a little bit more efficiently. Instead of a calculator, we can use a spreadsheet as a glorified calculator, still doing it by hand. And then eventually, we'll also demonstrate how we can use dedicated statistics software like SPSS to streamline it even further. But in the beginning, it's very good to do things by hand, to really go at a slower pace, sort of force yourself to see what are the pieces and the steps and the procedures here. All right, so we are going to use this book, Statistics for Psychology, for our examples. Simply the book I have available to show on the screen here. You might have a different prescribed textbook, really doesn't matter. They are all very similar. So we are going to go to page 577, and we're going to look for number 13B. Oh, I have it right there. Just zoom in a little bit. 13B. Okay. So we want to carry out a chi-squared goodness of test for goodness of fit for the B one because it's a little less to do by hand, a little easier. And we have three categories, and we have some observed scores here. We want to see if it fits a distribution where the probabilities are third, sixth, and a half. All right, so let me quickly write that down. Could have done that from the start before I started the video, but I didn't. So we have some observed scores here, A, B, and C. Not a lot, because we want to do it by hand. Having too many of these is just quite tedious. So we are going to look at the expected. Now, this is going to be, if I bring back my book here, my question, we expect a third of the total, a sixth, and a half. So I need to sum this up here. Let's add these together, super easy. So it's going to have to be a third times the total. So these numbers are set up to be easier to do by hand. So we have our 10. This one is going to be a sixth times the total, which is 5, and a half for the last one, which is 15. And you can check that they do add up to the same total number of scores, as they should. So now, let me remind you the formula that we're ultimately aiming for is this one over here. We're building our chi-squared statistic, and we're looking at observed minus expected, squaring those differences over expected for each one, and then we'll add them all together. So let's move towards that. Now you can break this up into more columns here. It's just more work to do on the calculator, or you can go right away to the very last one, difference squared over expected. I'll do something in the middle, I think, because the difference here is pretty easy. It'll streamline our calculations a little bit. Observed minus expected for the next one is 5, and for the next one is -5. But I don't want to have too many columns here, one for squaring, and then I divide, because it does become quite tedious. So let me emphasize here how we'll do that on the calculator. Even though it's a 0, I'll show here what we do. the observed score is 0. And then, I know I don't need the brackets or anything. Divided by the expected 10. I know the answer is going to be 0, but just to show how we're using our calculator. Then we'll do the next one. Observed minus expected is done for us, 5, and then I square that, divided by the expected, which is also 5. So very easy numbers, so we don't get sort of clogged up with having to round everything and then rounding errors propagating. Those things can get quite out of hand, which is a downside of having to do it by hand. We just want to get a feel for the process first. So these examples are really good for that. So the next one is the difference of -5. Oh, it includes the brackets for me. That's nice. Extra brackets never hurt anyone. Divided by the expected 15. We'll round that one to 1.67 just for convenience. And now we have to add these together. So let's reset that. And we'll obviously get a 6.67. This is also our chi-squared statistic, according to the formula, right? That's all we need to do. It's quite simple as far as these guys go. So I'll write it over here again. Our chi-squared observed is 6.67. Remember, our degrees of freedom is 1 less than the number of categories, so 2 in this case. And now we have to visualize what's happening here. Or maybe state the null hypothesis. That would be maybe better, right? Null hypothesis over here. I'll just do it in words that let's say the population fits the distribution that I'm testing against. I have a sample from that distribution, and then the research hypothesis does not fit the distribution that I'm testing. So we have, let's visualize here our chi-squared distribution, like so. Get a little graph going here. So I'm observing a 6.67. But I want to decide, okay, I'm going to consider values as being in line with the distribution of a third, a sixth, and a half. Because I'm going to get some randomness. I'm going to get some variation from the ideal expected numbers up to a point. And the right, what's our cutoff? Our significance? 1%, 1% significant. So I'm going to consider it a little suspicious if I get something so extreme in the extreme top 1% of samples that I could get. That is going to be considered as strong enough evidence that if I get something out here past my cutoff, chi-squared cutoff, then that's probably because it does not fit this distribution here. And there's actually another distribution that this population follows because it is so rare to get this. But I have to find my cutoff value that I'm going to use first. So we have some tables we can look up. We're looking at the chi-square distribution, 1% alpha. Let me zoom in on this for sure for you. Boom, boom. I need to just get my hand back. Like so. That looks way better. So we're going to go degrees of freedom 2, 9.211. So our cutoff, 9.211. Let's write that over here, 9.211. And we got an observed that is only 6.67. So according to our choice here of our significance level, what we'll consider extreme, this is not that extreme. This could happen just by chance, still following this distribution. So we will make our conclusion. I'll write two versions. One is sort of referring to the hypothesis testing procedure and the variables and the symbols. Since my observed score is less than the cutoff, we do not reject the null hypothesis. So that's sort of the more statistical way of saying the conclusion. I also like to write the conclusion as if, now this one doesn't come from necessarily a word problem, but they sometimes have more flavor and more background to them. And I want to say it in more plain English, essentially. So we can say the evidence is not strong enough to suggest that the population that the sample comes from follows a different distribution. Or you can say it in many other words. The evidence is not strong enough to suggest that the distribution doesn't fit, or something like that. All right, so that concludes our first example, the chi-squared goodness of fit example.
Welcome to MathCats, where we aim to better understand mathematics. Join us weekly for discussions on elementary, high school, through to university math. You can request the next topic by leaving a comment on our YouTube channel or by emailing us at mathcats314@gmail.com. And as always, remember to like and subscribe. Thank you.